these questions are so, yeah. Okay, so this question, we have an object falling. Let me get back to, oopsies. So an object here is falling from some height h, we'll call this object mass m, and it's falling some vertical height h till it hits the ground. Which of the following statements is true in this situation? And yeah, my wife is asking me about paying for Cooper's preschool. So yeah, you get to see that. Enjoy. That's the joys of life once you get out of college and have a family. So which of these following statements is true? Now, we'll assume that more than one could be true, so let's just take them one by one. The kinetic energy of the object is decreasing. Well, that is plainly false. It's false, because it was all potential energy at the top, and that potential energy is going to be converted into Ke as it falls. At the bottom, it's going to be the maximum Ke. So the kinetic energy is absolutely increasing. The total energy of the object is increasing. Well, that's fake news. Because the total energy of the system is going to remain constant because we are neglecting air resistance, by the way. So there's no loss of energy to the system, which means that whatever total potential energy you have is going to be converted into Ke. All the way through here, it's going to be a mixture of Ke and Pe, but the total amount of energy is going to stay the same. Next thing, the potential energy of the object is increasing. Well, that's wrong, because potential energy, again, is mgh, and if h is decreasing, that means the potential energy is decreasing. The total energy of the object is decreasing. What? No way. Because as I just mentioned earlier, it's assuming that we are neglecting air resistance. That means that the system is not losing any energy, which means the total energy is consistent. It's the law of conservation of energy. Last one. There better be a true statement here somewhere. The potential energy of the object is decreasing. The kinetic energy, yay! Okay, so we will definitely say that's true, and smiley face, and true. Because the potential energy is going down, and that's being converted into kinetic energy, which means the velocity is increasing. And so, yes, the potential energy is going down as the kinetic energy goes up. Okay, so you have mass attached to one end of the string. The other end of the string is attached to a rigid support, and yada, yada, yada. You drop it at A, and it's going to go wee. It's going to swing through B all the way up to point D. And beyond. How do you know it travels beyond? Well, I'll get to that. So the question really is, at what point does the mass have the most potential energy? But I decided to answer this question a little bit differently. I'll get to that point, but I want to make some bigger points about potential energy and kinetic energy that might help you on future questions. But I'll maybe also just give you just a general understanding of what's happening here without just being like so limited to me just answering the question. Okay. So what's happening here is that if you simply release it at point A, that means that the initial velocity at point A was 0, which means that all of its energy was potential energy. So we'll say potential energy, I should probably get that smaller, was at a maximum here, and the kinetic energy was 0. Again, because you released it, meaning the initial velocity was 0. The potential energy, a reminder, is mgh, and this h is the vertical height that something will drop. So the h, the potential energy at A, really comes from this distance from here to here. I'm trying to make that even with C, by the way. Because that's the only vertical distance that it could fall. Now, who knows? Maybe this little pendulum is like on somebody's desk, or it's on the 35th floor of a building, right? But since the object can only fall the vertical distance from A to C, because it's attached to the string, that's the only potential energy that we care about. Because it can't fall all 38 floors and go faster and faster because it's attached to the string. So all that potential energy is totally irrelevant to this system. The potential energy is only the vertical between A and C. So at point A, it has no kinetic. It has the most potential, at least so far at this moment. At point C, I'm going to jump down to point C now. At point C, it has fallen the farthest it can fall, meaning that now at point C, its potential energy is 0, because again, it cannot fall any further. It's attached to a string. If all the potential energy is 0 now, that means that all the previous potential energy must be converted into Ke, which means that Ke is a max here. Or another way of saying this is that at point C, it's traveling the fastest that it's going to travel. And honestly, even an 8-9-year-old kid can tell you that it's going to go the fastest at the bottom of the swing. But this is just the physics reason why. So again, it starts off with 0 kinetic, and it's all potential. And that potential is tied into the vertical height that it can fall. At point C, all that potential has been turned into kinetic, so the potential is now 0, and whatever it had for potential before is now all kinetic, so it's traveling the furthest. Points B and D. It's kind of hard to tell, but let's just assume for a moment that these are supposed to represent the same height. What that tells you is that the potential energy for both these is the same, assuming that they're at the same height. And they're kinetic, because they still have some potential energy to fall, their velocity is not at a maximum, right? They can still convert some of that PE into KE. They definitely have kinetic energy, though, because they have converted, this much into kinetic energy, so they have some kinetic energy. But again, that amount's the same for points B and D. Again, assuming that they're at the same sort of vertical position here. They both have this exact same velocity. It just so happens that B, that velocity is directed down at an angle like this, and at D, the velocity is directed up at an angle like this. But whatever number that velocity is, that number is going to be the same. Okay, now to answer the actual question here. It says, at what point does the mass have the most potential energy? Again, potential energy is tied into the vertical height, and so the greatest potential energy would be here at A. Okay, so question 3, we have a horizontal spring at the end of an amusement park ride to bring a car to a stop. So essentially this is what's happening here. We got the car here, and then we got some type of massive spring here. And then the spring will compress. Hey, my friend just played a chess move. The spring will compress until the car comes to a stop. So essentially this is a work and energy type of a problem, because the car has kinetic energy, and the work done by the spring will take it all away until the energy equals 0 at the end, right? Because the car is stopped. So what we got to do is think about the kinetic energy of the car, which is going to be 1/2 mv squared. Now the work done by the spring is going to take all that away until the car is motionless at the end, or until the car has 0 joules of energy. So basically another way of saying this is that the kinetic energy has to be equal to the work done by the spring, right? So now let's just plug in some equations. So 1/2 mv squared is equal to 1/2 kx squared, because 1/2 kx squared is the formula for the work done by a spring. And if, again, there's a derivation of that if you need to see it, but it has to do with the area under a force triangle for the force of a spring. And okay. So there's 2 ways to do it from here. There's an easy way and an even easier way. So let's just start with the easy way, and then we'll do the even easier way to double check. The easy way is just to plug in the numbers that are given and to figure out what the new value for x will be. Now, the first thing you got to notice is that you have to solve for k, right? Because if we're looking for a new x and we don't have k, well, then we have one equation, 2 unknowns, and it's just not going to work. So first things first is let's get k first. So 1/2 times 255.1 times 3 squared, that'll get you the kinetic energy of the car, equals 1/2. Now we don't know what k is, but we do know that it compressed 0.79 meters in order to stop it, so it's going to look like this. Notice right away, cancel, don't even have to worry about those. You do a little bit of calculator work, and it turns out that the k value is 3678.74 newtons per meter. Okay, so remember the k value is a measure of the stiffness of the spring. So that k value is not going to change even if we double the mass of the car, right? It's still the same spring. So that K value now is going to be constant. So now the question is, how much will the spring compress if the mass doubles but the speed stays the same? So now let's just sort of take a look at the new stuff. Well, if you double, if you double the mass from 255.1, you're going to get 510.2, but you keep the velocity the same. Now the K value is not going to change because it's not going to change. Unless you wave a magic wand, I suppose, but we're not doing that. But we want to figure out what the new X value is. All right, and lo and behold, X is equal to 1.117 meters. So it's gonna compress even more, but it makes sense because the car is heavier, so it's gonna squish the spring even more before the spring is able to stop it. That was the easy way. The even easier way is to go back to, and I'll do this in purple, is to go back to this relationship here. That 1/2 mv squared is equal to 1/2 kx squared. The halves, if you think about this, that the halves go away. There's a half on both sides, so I'm just going to play with the algebra just a tiny bit here. Okay. Now, if we keep velocity the same, and we keep the spring the same, and we look for the relationship between the mass and the compression of the spring, you see that the mass is proportional to x squared. All right? So now, if you double, so remember, we're treating this like a proportion now. If we double the mass, what do we have to do to this side to get that factor of 2, right? Because if you multiply one side by 2, you have to multiply the other side by 2. So what if x is squared, what do you have to do to the value of x that if when you square it, you get a factor of 2? Well, that means that you need x to be a square root of 2. You need a factor of the square root of 2, right? Because if you square the square root of 2, you get your factor of 2, and that's exactly how much you adjusted the mass by. So there is a way you could have done this without even having to look for the k value, which is just to say, all right, whatever your original value of x was, multiply it by the square root of 2. And so 0.79, the 0.79 was the original value of the x. And if we multiply that by square root of 2, guess what you get? 1.117 meters. So this is probably the most obvious, straightforward way, the top one that I just starred, just to crank out a x or crank out a k value and then plug in some new variables. But you know, this other way is a nice way to check it, but it's also a nice way to just think about the relationship here between the mass and the compression of the spring. The mass is proportional to the square of the compression of the spring, and since you're doubling the mass, you better be the square root of 2ing, if that's a word, the square root of 2ing the compression of the spring.